size from tornadoes vary in size from, maybe a couple 100 yards wide or 100 yards wide, and a very, very large tornado might be a 1/4 mile across. And if you think about the size of the Great Plains, and if anybody's driven across Kansas or Nebraska or in Texas, you know just how large those our plains are. So getting to storm chase and find tornadoes is pretty much like finding a needle in a haystack. So tonight I want to do sort of 3 things. I want to talk a little bit about where tornadoes occur in the U.S. And when and why. And then I want to talk a bit about the kinds of storms that produce tornadoes. And then those are known as supercell thunderstorms. They're the most frequent producers of tornadoes. And that'll be a little sciencey with some maps and some graphs and that sort of thing. And then I want to tell a couple of stories about my most recent storm chasing experiences with students. And those are from 2017 and 2019, and was probably scheduled to go out last year, but we ended up not doing it. So we'll hopefully I'll get a chance to go out again pretty soon. Okay, so where are tornadoes most frequent? What you're looking at now is a map of the average annual number of tornadoes from 1985 to 2014 by state. And the red colors there in Texas, and I'm using my mouse. And so, 140 a year in Texas. And you can see, compare that to New Hampshire, where we have just on average 1 per year. So if you're going to go to storm chasing, you might want to go where the most tornadoes are. Now, if you are an astute observer of maps, you will know that Texas is quite a lot bigger than many other states. So maybe it's not surprising that Texas has the most tornadoes because it's one of the biggest states. So here's another map showing where tornadoes occur. And in this map, the color coding is the average number of tornadoes per year per every 10,000 square miles. And again, now you see when it is coded this way that Oklahoma is actually the center. Oklahoma and North Texas are the center of action in the United States where tornadoes are most frequent. And this area from central Texas up through Oklahoma, Kansas, and into southern Nebraska has a name. The meteorologists call that Tornado Alley. So this is the most frequent area of tornadoes. Then you'll see 2 other places where tornadoes are frequent, more on an east-west axis. And this area in Mississippi, Alabama, and Georgia is sometimes known as Dixie Alley. And then this area north of the Ohio River and south of the Great Lakes is another place where there are frequent tornadoes. And once again, if you look closely up here in New England, most of the area is fewer than 1 per year on average, where central western Massachusetts, southern Vermont, and very southwestern New Hampshire are almost 1 to 3 average tornadoes per year. Here's just another graph showing the density. These are all the tornado paths from 1950 to 2017. And it's just another visualization that helps you see where in the United States tornadoes are most frequent. And again, you notice the Northeast, not very frequent, but more frequent in southern New England than here in northern New England for sure. And very few tornadoes similar to New England in the western United States. And just zooming in on New Hampshire, this is a map showing the locations of 60 years. That's 60. I can do math. 60 years of tornadoes. The numbers that you're seeing on these little dots here are the rating, the strength rating of the tornadoes. So a 0 is a very weak tornado, and the categories go up to 5. So an EF5 would be the most violent and strong tornado. And I think you can see that by and large, southern New Hampshire is where you get a few tornadoes. And by and large, they are not major tornadoes, generally weak on the tornado scale. So moving along. Okay, so we know where tornadoes occur climatologically now. Now let's figure out what time of year we want to go and think about doing tornado chasing. And this is the number of tornadoes by month over, again, a 61-year period. And it's pretty clear that May is the winner. There are the most tornadoes in May, and the second highest month is June. So late spring is the maximum for tornado occurrence in the United States, but you can get tornadoes year round. And in fact, we'll see evidence in just a minute that just this past December, right, there was a very devastating tornado outbreak in the Kentucky area. And that, so you can see that, you know, the US is not out of the woods in December. Of course, New Hampshire is out of the woods in December. We don't get tornadoes in December. All right, what time of day? So this is a graph, again, of the sort of normalized occurrence. That means the when are the tornadoes most frequent and what time of day. Midnight is over here on this side, and 11 to midnight is over here. So you have 24 hours. And the maximum, again, is between 4 p.m. and 6 p.m. Or 7 p.m. local time is when the most tornadoes occur. And that sort of makes sense. We know that thunderstorms usually happen in the afternoon. Tornadoes are associated with thunderstorms. So it might not be surprising that they would happen in the afternoon, but it's the late afternoon that really is when tornadoes are most frequent. And we'll talk a little bit about that. Once again, though, you can get tornadoes any time of day. So there are tornadoes that occur in the middle of the night, and those are really rough for both the people that experience them because it's dark and it's hard to see them. And just to show you what last year looked like, these are the locations of tornadoes in 2021. And it follows the pattern pretty closely. I think most of Tornado Alley had a few, but probably less than normal. The activity was shifted a little further west last year. And again, you can see these clusters of thunderstorms in Dixie Alley, and in particular, these storms here in Tennessee and Kentucky that were associated with that December outbreak. All right. So I'm going to stop there. Well, let me just finish this thought. So when are we going to do storm chasing? Where and what time of day? So if you really want to observe tornadoes, and the reason to do that is scientifically is to match what people are seeing on radar with what's visually being observed so that you can improve tornado forecasting. So where are you going to do that? You're probably going to go to the South Central Plains. And what time of year are you going to do that? Probably May or June. And what time of day will you be out there? Mostly late afternoon. And I'm going to stop there and see if there are any questions.
So I don't see any questions in the chat just yet, but.
Okay. Again, feel free to drop questions in the chat, and Amanda will help me if those come up. Okay, so now we know what we're going to do. When we get out there, what are we going to look for? And the answer is we're going to look for thunderstorms that are called supercell thunderstorms. And I'm going to try and here's where it gets a little sciencey and technical. So stick with me for this part, because we'll get to the stories in just afterwards. But a large majority of tornadoes occur with a storm type called a supercell thunderstorm. And supercell thunderstorms are known to have rotating updrafts. And I'll try and explain how a thunderstorm develops a rotating updraft. And it's through this tilting of the environmental wind shear. And once updrafts are developed in a thunderstorm and downdrafts start to form, that is when you can get tornadoes. Okay, so this is a graphic showing sort of a cross-section, a vertical slice through the atmosphere in, say, the lowest maybe 8 to 9 kilometers. So the bottom of this picture is the ground, and the top of this picture is near where jet airplanes fly. And the environment in which tornadoes form have wind shear. That's wind going at 2 different directions. So these red arrows, this one right here is sort of at low levels going into the screen. And the red arrow above is going across the screen. So you can imagine that there's wind at 2 different levels. That wind shear produces tumbling motion in the atmosphere, rotation. And then when you develop an updraft, which is rising air in a thunderstorm, that can tilt that rotation into the vertical and produce a rotating updraft. Here's just another way of looking at it. Again, very often you have southeasterly winds at the surface coming in at low levels, and strong westerly winds from the west to east at upper levels, producing this kind of rotation in the environment. And then when you superimpose an updraft on that rotation, then that gets tilted into the vertical. And just so that you might get a chance to look at it, I'm going to stop share for a second, and I'm going to use a cardboard tube with arrows on it. And we're going to imagine that the air at low levels is coming this way. Sorry, nope, this way. And air at upper levels is coming that way. And that produces rotation. I don't know if I got that right on the screen. But anyway, there is rotation in the, and that's sort of happening because that's just what the winds are going to be like that day. And then along comes the afternoon heating, and it produces some clouds, and the clouds have updrafts, and that updraft tilts that rotating column into the vertical, and now you have air that is rising and rotating. Rising and rotating. I don't know if that was effective, but maybe it was. Hopefully it helped a little bit to visualize. Okay, and let me share again. Are we back? Amanda, does that look right?
I can see the presenter notes.
Oh,
this
see?
time.
That's odd. Let me make sure I do this the right way. Let's share.
Perfect. I can see them now.
Now we're good. We're good now.
Now I can just see you. I can't see your screen anymore.
Oh no. Technical difficulties. Okay. Slow down, click slower. And now.
Perfect.
Thank you, Amanda. Sorry, everybody. Okay. So I'm going to show a couple more diagrams. Again, the reason we go out and observe storms right up close and personal, I mean, there is a thrill factor that you can't deny, but the scientific reason is to be able to match what you're seeing from radar and satellite images with what's on the ground so that you can understand the storm structure so that you can then make predictions and improve warnings. So these schematics of that rotating updraft and the flow around these thunderstorms, were developed by scientists who went out in the field and observed thunderstorm structure and compared them to radar. So just quickly, you've got flow coming into the thunderstorm, being tilted up and rotated into the pink updraft here. The flow at mid levels is coming from this way, and it has to split and go around the updraft. And when it comes back together, you can produce some downdraft here. And this is cool air that formed from evaporation of raindrops in the thunderstorm, which spreads out along the ground. And then you even get an updraft from the very upper level flow, sorry, a downdraft from the very upper level flow that develops on the backside of the storm. So the storm has sort of three big pieces: a rotating updraft, a forward flank downdraft on one side of the storm, and a rear flank downdraft, which develops a little later on the backside of the storm. And when the storm develops this structure, that is when you can observe tornadoes. This is a graphic looking down from overhead, and it would be what the radar would show. So this black outline is the area that the radar would show the heaviest precipitation. And there are two parts of the thunderstorm where there's danger for hail. Supercell thunderstorm in this downdraft region here, and in this downdraft region here. And I know it's quite small, but I've tried to put a green arrow in it. This little T is where the tornado usually forms. And this is known as a hook echo because there's a little hook in the diagram here where this little appendage sticks down this way in the radar presentation. And that tornado forms right in the crook of the hook. And so when you are storm chasing, what you're trying to do is you're trying to position yourself here where there's usually no rain, and maybe you're under the cloud, but there's no rain, and you can see and observe what's happening in the area of the tornado, but you're not experiencing large hail from either of these two regions of the storm. And the idea, if you're doing it safely and carefully, is that you are here observing and you are moving with the storm. This storm would be moving off to the northeast in general. So when we're out there chasing, we're looking for radars that have these little hook echoes because that's showing the rotating updraft. And that's where we think we might find a tornado. Here's a more modern look of that. So again, this is a very similar picture to what I just showed you, showing a few more features, but the hook echo, the tornado in the center, and this storm traveling off in this direction. That rotating updraft is called the mesocyclone. And it is not the tornado, it is just the rotating updraft. And that extends up to 6, 7, 8 kilometers above the ground. And you can see the hook echo on the radar here, the regular radar reflectivity. And then Doppler radars can also show the winds in a storm. So that's why Doppler radars are useful. And reds, the radar in this case is down in this corner, and reds indicate flow that's going away from the radar, and greens indicate flow that's going toward the radar. And so when you see red next to green right here, that is indicative of the rotation in the thunderstorm. So this thunderstorm has a rotating updraft. And when we're storm chasing, that's what we look for. Here's what it might look like if you're looking at the cloud from far away, maybe 20 miles away or so, maybe 10 miles away. That's the beauty of also being out in the plains, is there's no trees and mountains to get in the way of your view. So you can see the storm structure from a long way away. So very typically we have this big thunderstorm cloud with an anvil that might be extending 10s or 20 miles away from the action here in the rotating updraft. Once the storm develops, it can have this lowering of a cloud below this base here, and that is known as the wall cloud. And once you see a wall cloud, then you might begin to look for the tornado to form in that region of the cloud. So we'll come back to this picture a little bit later, but that's sort of what the storm structure looks like. Okay. So from storm chasing, right? What are we going to do? We talked about where and when, and we're going to go look for storms. And when you're out there and you're trying to understand the science of this and do a little thrill seeking, I have to admit, then your goals: find a rotating thunderstorm, find a supercell, observe the storm life cycle from beginning to end if you can, from a safe distance. And if you're lucky, you get to observe a tornado. All right, are there any questions that have come up now?
There are none in the chat, but we could give people a moment to
Sure.
think about it if you'd like.
And if you want to hang out to the end too, that's okay. Either way, I'll be sure to answer questions, but we can give folks a minute. Give me a chance to get a drink of water. Okay, so now we get to the cool picture part of the presentation. Unless was there half a thing coming in the chat, Amanda, maybe?
Okay, one just came in.
Okay, cool.
Someone asked, what has been the scariest situation you've ever been in weather-wise?
Ooh. All right, that's a great question. Scariest situation I've ever been in weather-wise. Me personally, we were launching weather balloons in the very bad and wind rainstorm from October about 5 years ago. And in the middle of the night, because that's when the storm hit, and we wanted to measure the atmosphere in the middle of the storm. And so I left my house and trees were falling across the road and the power was out. And I was questioning whether I really should be going out to do this. And so that was probably the scariest thing that I've done. So surprisingly, it hasn't been storm chasing. So, okay, some cool pictures. What does a rotating thunderstorm look like? Might look like that. Might look like this. And I hope you can see that you can, these are well above the ground, so you can drive right underneath them. And sometimes you do. First time I went storm chasing, I was out with some friends who had done it before. And I kept saying, is that a rotating thunderstorm? Is that a rotating thunderstorm? And the quote I got back was, if you have to ask if it's rotating, it's not rotating. So hopefully this image is a little sped up, right? But the point is you can observe the rotation visually with your eyes. So if you have to ask, it's not rotating. Here's another one. If you have to ask, it's not rotating. So, and again, this is not the tornado. This is the large rotation in the updraft. The tornadic rotation is something else altogether. So, yeah, here's some pictures of tornadoes. Tornadoes come in all different kinds of shapes and sizes. And do I sense a question?
Yes, there is a question.
Okay.
So someone asked, how does climate change affect tornadoes? Will they move north?
Ooh, that's an excellent question. And an area of active current research. So climate change is happening on a global scale, and tornadic thunderstorms are on a small scale. So how the connection between the large scale and the small scale is not as simple as this X leads to Y. So the climate change community is, and everybody is obviously interested in that. So I would say it is not clear whether it will move further north. or what the exact change will be to the frequency. I think, the more warm, humid air masses that are a little bit further north have the potential to increase tornadic activity. But that's kind of a wild guess on my part. So I'm going to stick with the active. It's an area of active research.
And then before you go on, we have another question too.
Awesome.
So another person asked, if I see an anvil cloud formation, like in the illustration, could I tell that that's a severe thunderstorm is coming, or even a tornado?
Well, you wouldn't be able to say there's a tornado, but a thunderstorm cloud with an anvil developed like the one I showed is most likely to be a severe thunderstorm. And might have just strong winds, it might have hail, or frequent lightning, even if it doesn't have a tornado in it. So yes, if you see those well-developed anvils, it's usually an indication that the updraft was strong enough to reach all the way up to the jet stream and then spread out along the jet stream. So that is usually an indication that you've developed a strong updraft. It could be an indication that the storm is severe, but not necessarily. But it would be, you would experience it as a strong thunderstorm. So that's the best I can do. All right, couple more pictures of tornadoes. Oh, this one, your curlicue, your stovepipe tornado, and then there's another classic sort of stovepipe tornado. Okay, story time. We're going to start with reality. Then we're going to talk about serendipity and the fact that I wasn't there for it. But anyway, reality. Storm Chase 2017. I have colleagues who teach at Hobart and William Smith Colleges, which is in Geneva, New York, in the Finger Lakes. They host a field course for students called GO 299. It's a storm chasing field course. And they've invited me to go along a couple of times. And I was happy to do so in 2017. We had 4 faculty instructors. We had 14 students, so 18 of us total. That means 9 of us each piled into a 10-passenger van, and we went out storm chasing to observe storms and learn about how they form and to get students to be able to see those kinds of storms up close and personal. We were out for 10 days from May 20th through the 30th in 2017. This is where the tornadoes occurred in 2017. And our target area, of course, was the Southern Plains. And there were plenty of tornadoes that year in the Southern Plains. But this is a diagram that shows the cumulative number of tornadoes for the year, starting on January 1st with 0, and then you just keep adding them up. And the red line was the 2019 values. So you can see at the end of the year, there were 1,522 tornadoes in the United States, which is slightly above average. The red vertical bars are the number of observed tornadoes. And May 20th to May 30th was right in here, where you see very few red bars. That was when we were out storm chasing. Too bad. So we're, in the end, I'm going to show that we didn't see a tornado. We saw lots of cool storms, but there also weren't that many tornadoes to see in the US during the time period we were out there. But we still it had a good educational experience. Okay, our first day, we were starting in the Finger Lakes in Geneva, New York, and we drove from there to Indianapolis in one day. And we pulled into Indianapolis, and we went out to dinner, and my faculty colleagues and I were sitting at dinner and we're watching the news, and lo and behold, there were tornadoes right outside Indianapolis that day. But we are glad we didn't try to chase those because it was late in the day and there was traffic, and it was in a suburban urban area. So chasing in traffic is no good. Oh yeah, here's the crew. there's all of us outside the two vans. Just that was when we were all happy and we were not realizing how much driving we're going to do. So there we all are getting in the vans. There's a picture of me driving one of the vans, and all the students in the back, crammed into the back. Again, smiling faces. It must have been one of the early days. We had a good time most of the whole way through. Here's that. Here are the storm reports from the day of our trip from Geneva to Indianapolis, and there are the tornadoes that were in the Indianapolis area that we did not try to chase, so we missed them. Okay. Next day was another travel day. We knew that in a couple of days there were going to be storms in West Texas and New Mexico. So we needed to get to West Texas and New Mexico. So we drove from Indianapolis to Oklahoma City in one day. It was about 12 hours in the car. It was a very long day. And that was what we did on travel day number 2. All right. On day 3, we started the morning in Oklahoma City and we drove to West Texas. We thought the storms were going to form near Lubbock. And it turns out that the best storms were over in eastern New Mexico. So we drove all the way to eastern New Mexico to intercept storms. Now, if anybody has watched television storm chasing shows, it might look like it's kind of fun and you're having a fun day all the time. But here's what a typical storm chase day looks like. Get up in the morning around 7. College students love that, by the way. Eat breakfast, do some forecasting. From 8 to 9 a.m., the students led forecast discussions. They had 2 things to consider. What was that day's chase plan? Like, where were we thinking the storms were going to form so we could go find them and intercept them? And then we also had to think about what would tomorrow's chase day look like. Because when the day is over, you got to get yourself ready to storm chase the next day. So you have to do both forecasts. Depending on how close you are to where the storms are going to initiate, it might take 3 to 4 hours of driving. So you drive for 3 to 4 hours. And then you find storms and you drive for 3, 4, 5 hours until it gets dark. And then you decide, okay, and then you have to drive for a couple more hours to get ready for the next day's chase. And around 8 o'clock, you're usually getting dinner, and then you start forecasting for the next day again. And do that 10 days in a row. So it's not glamorous. Storm chasing on TV looks glamorous. It is not. But anyway, we got out to eastern New Mexico and we saw a gorgeous storm. It was beautiful. It had great storm structure. It had everything but a tornado. And here are the students out there taking pictures. This was a shelf cloud and there was rain and hail over in here. And this was coming, the storm was coming at us. So we were sort of sliding out of the way of it. So we didn't get hit with any hail. And lo and behold, here are the storm reports for that day. No reds. Reds are tornadoes. So eastern New Mexico, there was some hail and some high winds. We were here. We did not see a tornado. There was no tornado to see. The cold front came through. No storms for 2 days. So we had down days, we called them, and we hung around in Amarillo, Texas, and then drove up because storms were going to form in a couple of days in Kansas, Colorado area. So we drove from Amarillo to Kansas, Colorado, and you can't just let college students sit around the hotel all day. So we did some fun things. We went out to Palo Duro Canyon State Park, which is this beautiful state park near Amarillo, did some hiking and saw these cliff formations. The next day we were at the Kansas, Oklahoma, Colorado triple point. So there's a marker in the ground where the 3 states come together, and there's this statue there. It is in the middle of nowhere. It's down like 12 miles of dirt road and farm fields on either side. But, you know, we were passing by, so we figured we had to try it out. And you can see Beautiful blue, clear skies, not a cloud in the sky that day. Okay. Day 6, we did some storm chasing in eastern Colorado and western Kansas. And we knew we were going in the right direction. When you see a car like that on the highway, you know you're going in the same direction as that car, the Dominator. That's a storm chasing vehicle from the Canadian version of the Weather Channel. So we kind of knew we were heading in the right direction if they were going the same direction as us. We also did some science while we were out there with the students. So here are students preparing a weather balloon for launch. Again, this was early in the day before the storms initiated. So we're trying to sample what the temperature and wind profile is in the atmosphere. And so we're down a dirt road launching a weather balloon. And then later in the day, we did intercept a storm. It was a pretty big storm. It developed real quick. It did not have a tornado in it, and it crossed right in front of us. So we had to let it go and then catch up to it. So here's a picture of that storm when we were trying to catch back up to it on the backside. Really dark clouds, some well-developed. There was some hail and high winds with this storm. I'm going to show you a couple of pictures like this. And this is a radar image from an app you can get on your cell phone called Radar Scope. And it is the radar reflectivity showing you where the heaviest rain and hail would be in the reds and pinks. The red boxes are tornado warnings. So this storm actually got a tornado warning, but there was never a tornado observed. And the yellow boxes are severe thunderstorm warnings. This blue circle is the location of where your cell phone is. So we were in vans and we were driving along this road to try and catch back up to this storm. And unfortunately, it was also getting dark. So we kind of we got up to the back of it and we're hoping to see a tornado drop down on the backside because it was tornado warned, and we didn't see one. But we did catch some cool pictures of these kinds of clouds, which are called mammatus clouds. So, and once again, there's the crew. We were pretty happy that day. Cool clouds made us happy. All right. The next day was the best chase day of the 10 days. We were in, that's showing that there were no tornadoes. Even though there's a red dot here, I guarantee you there was no tornado there. So we didn't get tornadoes that day. The next day we were in eastern Colorado. So we were chasing here in eastern Colorado, and we had fantastic storms, and they developed right in front of us, and we were able to follow along the storm. Here's one of the students. We were taking time-lapse photography on an iPad of the storm, and people were out looking at the storm as it started to develop, and then it was starting to produce some lightning, and we were starting to see some storm structure. And then we followed the storm for about another 20 minutes. And remember, I was telling you that there were clouds that are lower than the base of the clouds. So that's known as a wall cloud. And so this storm started to develop this inflow and maybe started to develop a wall cloud. It was definitely rotating. So we were very pleased by that, and we wanted to keep chasing it. So we chased it a little further, and you can almost see the rotation right in here. So this is again inflow into this lowering wall cloud. And so we were pretty close, and we were like, okay, this is it. It is going to drop a tornado. It's doing everything. We're in the right position. We're safe. And it looked great. Again, you can see the lowering of the cloud over here. Can people, Amanda, can you tell that it's kind of light blue where my mouse is there? Is that
Yeah,
good
you can
enough
see
on your
that.
screen?
Yep.
So when the clouds look like that eerie green or light blue, it's because there's hail. So this was indicative that there was pretty significant hail developing in this part of the storm. And remember, right, the backside of the storm is where you would expect the wall clouds lower and maybe get a tornado. So this storm was doing everything we thought it would. We're in position to see it. And we were sitting there watching it, and this feature dropped out the bottom of it, and it was rotating. And here's a different picture of it over here, the same feature, different lighting, different camera lighting. So there's this feature, and I'm going to just stop share for a second. So hopefully it won't mess everybody up. But this is about the speed of the rotation. It was maybe spinning this fast. Really slow. It was not a tornado. I can guarantee you that. Nonetheless, somebody reported a tornado at that time from this storm. So are we back on the regular screen, or are we in presenter mode, Amanda?
Presenter mode.
Weird.
Guess it just doesn't like.
It doesn't like
going back and
popping
forth.
back in there, does it? All right. How about now?
That's perfect.
Okay, that is bizarre. So in any case, we were waiting. Notice that there's some more light blue in the picture and some rain coming. And we allowed this feature to get quite close to us. So we had to hightail it out of there because this hail was coming our way. So again, we're trying to be safe with our students and observe the storm from safe locations. So we did not want a large hail to bother us. So again, there are some red dots here. One of those was a report from that thing, and I can guarantee you that thing was not a tornado. Nonetheless, this also went into Western Kansas. Okay. Next day was another good chase day, and we ended up staying the night in central Kansas, and then we had a decision to make: were we going to storm chase here in Kansas that day or southern Oklahoma? Southern Oklahoma had some of the best conditions for tornadoes that I ever have seen, except they were going to form late in the day. And there was some chance that they might not form at all. But if they form, the conditions were perfect for tornadoes down here in Oklahoma. So that's where we chose to go. And we got into a storm. The storm was rotating. Once again, we were in perfect position to see the wall cloud. And this is sort of just showing the scale of how big this cloud we're in underneath, and no tornado. And just to show you how perfect the storm was, this is that hook echo in the radar. Can you see this little hooky thing back there? And we were right in the slot on this road that went north-south, and we were looking right into that part of the storm. No tornado. Oh, wow. And that storm hit quick. It spun up, did not produce a tornado, and died out real quick. And again, there were some reports of Doppler indicated tornadoes, but there were no actual tornadoes observed on the ground as far as we know. Again, this was kind of a big day. Lots of wind. There was big wind damage in Tennessee and Kentucky overnight that night. Okay. Then we chased in Eastern Texas the next day. It was kind of a lousy chase day. We let the students run the show completely. And then we ended up, there were no real tornadoes that day either. And then we headed home. Texas to Tennessee, Tennessee to Ohio, Ohio to Geneva. Put about 5,000 miles on the vans in 10 days. So maybe even more. So that was 2017. 2019, I couldn't go. They went out. They got in position for a storm on the 26th and saw a tornado. a very nice one. They were texting me pictures that day. And I was like, oh, I really wish I was there with you. The next day, 2 days later, again, they were in position for 2 storms, and they could actually see from where they were, they could actually see both storms at the same time. And they saw tornadoes from both storms. There's one, there's the other, kind of off in the distance there. So just goes to show that it is hard to find these tornadoes, and sometimes you're out there and you do everything right and you don't see anything, and sometimes you're out there and you do everything right and you do see things. So and those were the storm reports from the day they were out there. All right, wrapping up. The reason we go out there and do this for educational reasons and for scientific reasons is to hopefully improve warnings and be able to understand how tornadoes form and how we can, help save lives and property. It's hard work. It's not glamorous, but it's worth it. And even if you're out there and you don't see a tornado, just being out and being able to observe these storms, which we can't observe very well here in New England, is really great for me. So, all right, I'm going to stop there and take questions.
Perfect, thank you. So we have a question in the chat. It says, why is the cone area of the tornado wavy and not straight up and down to the land?
The cone area of the tornado.
Yeah.
Why is it wavy?
Yeah.
When the circulation of the tornado spins up, there is still wind that is affecting and blowing it. And it might tilt it over this way and tilt it back that way. And so there is the interaction between the circulation of the tornado itself and the wind locally being produced by the storm and being produced by the environment. So some tornadoes, that rotation is very straight up and down, and it's, and others have that wavy appearance to it. The ones that are straight up and down are usually stronger rotations because they're more immune to the influences. So I guess that's my best answer to that question.
And then what prevents us from getting bad tornadoes in New Hampshire?
That is an excellent question. Okay. So sort of 3 things. The first is you need to produce big thunderstorms, you need warm, humid air masses. And we're talking Texas, Oklahoma, Georgia, kind of warm, humid air masses, which we get for a few days in the summer, right? Where it's unbearably hot and unbearably muggy, right? We get those just every once in a while, whereas other places in the US, that happens kind of all summer. So that's one. There are some geographical regions. We're very close to the very cold water of the Gulf of Maine. So sometimes that influences certainly the eastern parts of New Hampshire. The mountains can interrupt thunderstorm circulations. So mountainous areas are not often associated with tornadoes. In the springtime, when the jet stream is still fairly strong, we don't have those warm, humid air masses. We get those warm, humid air masses in the summertime. And so that environmental wind shear that you need to produce a rotating thunderstorm is not as strong in New Hampshire in the summertime. So we don't have the best setup. So it takes sort of the perfect, I guess, if you would, it takes just the right set of ingredients to produce tornadic weather here in New Hampshire.
Awesome. We have a little bit of a story / question. It says, one time when I was living in Illinois, I accidentally drove out into a severe storm. The sky was calm when I left. It turned out there was a tornado in our town while I was driving. Suppose I ran into it. What should I have done?
Oh, that's a really good question. And if you've watched any of these storm chasing videos, there's a couple of things not to do. Um, uh, One would the best advice is to not try and outrun it with your car unless you really know what you're doing. So the best advice, if it's really coming at you and you're in the car and you are not going to be able to avoid it, is probably to get out of the car and get in a ditch or as low as you possibly can get, because the tornadoes have stuff flying around in them, and that's what damages things. So it's the flying debris that is deadly. So getting as low as possible, it gets you out of any of that flying debris. So it might be counterintuitive to get out of your car, but that's certainly it. And you don't want to try and like get in your car to outrun a tornado. That would be bad. There was a video of people climbing up underneath the girders of underneath an overpass once, and that's also a really bad idea. They got really lucky that none of the flying debris got in where they were hiding. And that tornado actually missed them mostly in that video. So yeah, get as low as you possibly can is the answer. And if you're in a building, you want to be in an interior room without windows, or if your building has a basement, right? Get in the basement interior place so that you're not going to be hit with flying debris.
And this kind of ties in with this last question. Did you have an emergency plan set up while storm chasing in case you encountered a tornado in person in actual time?
Yes, I think in the sense that you probably mean it, yes. We were intending to get close to tornadoes. But we also were respectful of the distance. And if you are storm chasing correctly, then we train the students to be really good at mapping and driving directions. If you're a driver of the vehicle, your only job is to drive safely. Right? You're not supposed to be looking at the storm. You're not supposed to be doing any of that stuff. You're supposed to be driving safely. The map readers are supposed to know which roads could get you away from the storm. So which way the storm is moving, and you're always supposed to have a way to get away from the storm, drive away from it, and not in, so that you don't have to drive in its path. So our emergency plan was not to be in the path, and to do as much as we could to make sure that didn't happen. Yeah, that was probably the extent of our emergency plan.
And someone asks, how heavy an object can a tornado pick up?
Oof. So if you've seen the movie Twister, it's Hollywood, but it's not terribly Hollywoodish with the kinds of things that can get tossed around by a tornado. Large trees can be flung into the air, hundreds of feet. There are pictures of 2x4s going through walls and being implanted into telephone poles. A large tornado, the scale of tornadoes is based on their damage, and a large tornado will basically take everything off a foundation and scatter it everywhere. Cars can be lifted and flipped. Pretty heavy things can get moved by a large, devastating tornado. Smaller tornadoes, they knock down trees, they rip off roof tiles, they're annoying and do damage, but not that kind of stuff. But could happen, large vehicles can get, lifted in the air and moved hundreds of feet.
So it looks like we have time here for a couple more questions. So what inspired you to go into this field?
Good question. If you talk to any meteorologist, 98% of them will tell you some weather event that they experienced as a child was what got them into the weather. For me, I grew up outside Buffalo, and it was a blizzard. It was the blizzard of 1977. So I'm guessing many of you remember the blizzard of 1978 in the Boston area, but this was the Buffalo area, and we got our blizzard the year before. There was about 3 feet of snow, and then the wind came and it blew all the snow from Lake Erie into and around the city of Buffalo. There were drifts up to the second stories of buildings. We had a week off from school, and then the boiler in my school broke, so we had another week off from school. So 2 weeks off of school and more snow than I knew what to do with to play in. That got me interested in the science.
That is awesome. That sounds like a great fun to be had outside.
Yeah.
All right, so it looks like that brings us to the end of our questions here in the chat. And also looks like it brings us right to 8 o'clock, so that's perfect timing. I want to thank you again, Eric, for coming and doing this presentation for us. It was very, very exciting and fun to learn all about tornadoes and the trips that you've taken to see them. If anyone has any questions after the presentation is over and you'd like to get them answered, you can email education@starhop.com, and those will come right to me and I can forward them on to Eric and we'll get those answered for you.
Absolutely.
But thank you all so much for joining us tonight. This was a wonderful evening. I hope that you all have a great weekend. So
Thanks, everyone. Thanks for coming.
good night.
Bye.